जो व्यूवर्स या स्टूडेंट जो कनेक्ट हो गए हैं, काइंडली गिव मैसेज so I understand properly that some students are connected, and kindly give me message. Am I audible? मेरी आवाज पहुंच रही है? मेरी आवाज अगर पहुंच रही है तो आप मैसेज कर दें। अगर मेरी आवाज पहुंच रही है, ओके ओके, थैंक यू। टुडे our topic is carbohydrate, and the most significant feature of the biochemical significance feature of the carbohydrate is isomerism, because the carbohydrate is most abundantly observed biochemical molecules in the living system, as well as it has both structural, functional, and recognitional activities in the living system. And we are going to discuss on the topic carbohydrate. And we all know very well that carbohydrate is otherwise known as saccharides. And here the name carbohydrate, it is clearly represented that the carbon present in hydrated form. So it is referred as carbohydrate. Hydrated, that means the hydration means the H2O. So the carbon in the carbohydrates, the carbon, oxygen, and hydrogens are present in the ratio of carbon, hydrogen, and oxygen is 1:2:1, and 2:1 ratio of the water, so it is commonly referred as hydrocarbon. Hydrocarbon, otherwise referred as saccharides, and saccharides are naturally occurring polyhydroxyaldehyde and ketone. If we observe the functional groups present in the carbohydrate, then there are two functional groups present in the carbohydrate are aldehyde and ketone. So carbohydrate is simply defined as the polyhydroxyaldehyde or ketone in the carbon and H2O is present in same ratio. That is one carbon for one H2O. So here the empirical formula of the saccharides or monosaccharides, when the glycosidic bond, the linkage of the unit is not observed, so in this condition the empirical formula of carbohydrate is CnH2n OH2n or CnH2n or ON. In any way, it represents the empirical formula of the hydrocarbon. But when the hydrocarbon is combined, one hydrocarbon, that is one monosaccharide, is combined with the other monosaccharide, one molecule of water is removed. So in the disaccharide, the empirical formula is changed as CnH2O whole n minus 1, because in the association of two monosaccharides, one unit of water is removed. Likely in the condition of uh, trisaccharides, the two molecules of water are removed. So here the empirical formula is again modified, that is the CnH2O whole n minus 2. And likely in the tetrasaccharides, the empirical formula again change, and the empirical formula becomes CnH2O whole n minus 3. So when the monosaccharidic unit is increases in any polymeric form of the monosaccharide, the number of water is reduced less than 1 from the total units from the polymeric form of the carbohydrate. And on the basis of the number of the saccharidic units, the carbohydrates are grouped into monosaccharides, oligosaccharides. Oligosaccharides represent molecules 2 to 10, and polysaccharides. Commonly, more than the 5 unit monosaccharides are not observed in the oligosaccharidic units in a natural condition. Of course, the intermediate biochemical molecules are present which has more than the 3 units or more than the 4 units or more than the 5 units. But in the natural condition, the commonly observed or abundantly observed oligosaccharides are trisaccharides and tetrasaccharides. Of more than the disaccharide, trisaccharide, and tetrasaccharide are naturally occurring, in which the more abundant is the disaccharides, then the trisaccharides, then the tetrasaccharides, and more than the 4 units in any oligosaccharide units are not observed naturally. Where we consider the monosaccharide or disaccharide or trisaccharides, they represent two forms on the basis of the functional group. The monosaccharides having aldehyde functional group are referred as aldose, and the monosaccharides having ketone functional group uh, are referred as ketones. So the two forms of the monosaccharides are present in the natural condition, that is the aldoses and ketones. Some monosaccharides, in the monosaccharides, the lowest number of the carbon is 3, and commonly observed, naturally observed carbons in the monosaccharides are up to 6. So the monosaccharides are commonly named by the use of suffix OSE, OSE. For example, if the 3 carbons are present, then the monosaccharides are referred as trioses. If the 4 monosaccharides are present, 4 carbons are present, then the monosaccharides are referred as the tetroses. If the number of carbon in monosaccharide is 5, then they are referred as the pentoses. and if the carbon of the monosaccharide is 6 in number, then they are referred as a hexoses. The common trios which are observed in the biological system are glyceraldehyde and trihydroxyketone. And both the glyceraldehydes represent the aldogens and dihydroxyketone represents ketones. And both are observed as the metabolic intermediate products. Then the tetroges. Tetroges are observed sometimes in the natural condition, and the components are erythrose and erythrolose. Erythrose or erythrolose. Though both are the tetroges, erythrose is aldose form and erythrolose is the ketose form. In pentoges, we are commonly we studied in earlier classes, that is the ribose. Ribose is the aldose form and ribulose is the ketose form. And we all know very well that ribose is one of the key structural biochemical molecules in all nucleic acid, all types of nucleic acids. If we observe the 6 carbon monosaccharides, then variations are observed and they represent the isomeric nature which we are going to discuss today. And the hexoses, commonly observed hexoses are glucose, mannose, galactose, fructose, arabinose, fucose, that is the ketose form. And the fructose is also the ketonic form of the hexose monosaccharides. Now, if the monosaccharides are combined, then it forms the disaccharides. That means in the disaccharides, the number of monosaccharidic units is 2, and the most important observed, naturally observed disaccharides are maltose, trehalose, lactose, and sucrose. These components are these disaccharides vary on the basis of the monosaccharidic units. In maltose, the glucose, 2 units of glucose are observed. That means the maltose is formed by the condensation of 2 molecules of glucose. And second one is the trehalose. It is also formed by the condensation of 2 molecules of glucose, but the nature of bond is different in the maltose and trehalose, which we are going to discuss just uh, in this class. That the glucose and galactose, because in the carbohydrates 2 types of bonds are present, that is the alpha glycosidic bond. Of course, the bond formed by the condensation and the removal of the 1 molecules of H2O between the 2 monosaccharides is referred as the glycosidic bond. And on the basis of the orientational relationship of the molecules associated with the associated in the formation of the glycosidic bond, the bonds are of the bonds divided into alpha type glycosidic bond and beta type glycosidic bond. So here in the maltose and trehalose, of course, the monosaccharidic units are same. That is 2 units of glucose is observed in the maltose and 2 units of trehalose observed in the trehalose. 2 units of glucose is observed in the trehalose, but the nature of a bond is different in maltose and trehalose. The next one is the lactose, and in the lactose, 1 unit of glucose and 1 unit of galactose are condensed. Next one is the sucrose. Sucrose, that is the 1 unit of glucose and 1 unit of fructose are associated or are combines combined by the glycosidic bond to form sucrose. And it is the common malt sugar. In the malt sugar, maltose is present. In milk, the lactose is present. In cane sugar, sucrose is present. And triallose is present in the hemolymph of the insects. So here some informations related with the disaccharides. In the trisaccharides, the components observed naturally are monotriose. The monotriose is formed by glucose, 1 unit of glucose and 2 unit of galactose. That means glucose plus galactose are responsible for the formation of monotriose. In the next, that is ribinose. In the ribinose, galactose plus 2 unit of ramnose, 2 unit of ramnose and 1 unit of galactose are combined to form the 1 unit of ribinose. The next one is raffinose. Raffinose is formed by the condensation of 1 unit of fructose, 1 unit of glucose and 1 unit of galactose. Next one is the gentianose, and gentianose is formed by 1 unit of fructose and 1 unit of glucose and 1 unit of glucose. That means the 2 unit of glucose and 1 unit of fructose are responsible for the synthesis of or the formation of 1 unit of gelatinose. That means the monotriose, ribinose, raffinose, gentianose, all these four are included in the trisaccharides. The tetrasaccharide is rarely observed in the nature. It is not commonly observed, and two tetrasaccharides are considered here. One is stechiose, and stechiose is derived from the plant Stechis tuberifens. Stechis tuberifens is responsible for the production of stechiose, and second one is escardose. Escardose is present in the bulb of garlic and onion, and these two components are present in the form of tetrasaccharides. So here, if we observe the structural, if you understand properly the structural nature of the monosaccharides, because the monosaccharides are the structural unit of all carbohydrates, and after the formation of the carbohydrate, after the condensation of the monosaccharides, the different biochemical organizational components like the trisaccharide, tetrasaccharide, disaccharide, trisaccharide, tetrasaccharide, and last one is the polysaccharides. And polysaccharides are represented in the form of the glycogen, starch, cellulose, chitin, like this. And here, if we observe the monosaccharidic unit, then the structural formula is the cis polyhydroxy aldehyde and ketone. It is referred earlier today that the carbohydrate is the polyhydroxy aldehyde and ketone. That means at the carbon 1 aldehyde functional group is present, and all other carbon contains the OH and H, that is the polyhydroxy. That means the all carbon has the hydroxyl group, and in last the hydroxyl group is present. So here it is referred as the polyhydroxyaldehyde and ketone. And if in the ketone, then the second carbon of the monosaccharide mm, represents ketonic group, and while all other carbons represents the aldehydic, alcoholic or hydroxyl functional groups. So, in this condition, it represents the different natures of the isomerism. Of course, first we are discussing that the aldehyde and ketone the same molecular formula, and if we observe the isomerism represents the mm, same structural structural formula, mm, but they differ in the same structural formula, same properties, physicochemical properties, but they represent change in behavior in the biochemical systems due to the organizational variation either in the form of the configurational structure or in the form of the structural configuration or in the orientational, that is the spatial arrangement. In this way, they represent both structural isomerism, they represent the structural isomerism as well as the stereoisomerism. The both type of isomerisms are observed in the in the monosaccharides. So here, if we observe that the one carbon, that value is same, C6H12O6 for the glucose and C6H12O6 for the fructose. But if we write the structure, it is same for the glucose and the C6H12 is same for the fructose. But if we write the structure, then one glucose has aldehyde group and fructose has ketonic group. So here it represents the a type of isomeric nature because they represent the different natures in the physicochemical, biochemical properties. So it is referred as the structural isomerism. It is the structural isomerism. Structural isomerism is very simple, but in addition with the structural isomerism, the carbohydrates represent a stereoisomerism. It represents the stereoisomerism also. And the stereoisomerism is associated with the chiral carbon atoms. If the molecules represent, if the any biochemical molecules has the chiral carbon, then it represents the stereoisomerism. So, in this way, first you understand what is the chiral carbon. Chiral carbon represents, we all know that the carbon has the 4 valency. Each carbon, if you have the long chain, if you observe the carbohydrates, long chain carbohydrates or carbohydrates, each carbon has the 4 valency, and if the groups associated with the valency are different, then it represents chiral carbon. For example, suppose we represent CHClBi. C for carbon, H for hydrogen, Cl for chloride, B for bromide, I for iodide. And if we arrange this form, that carbon, one valency of carbon is associated with the hydrogen, one valency of carbon is associated with the chloride, one valency of carbon is associated with the iodide, and one valency of carbon is associated with the bromide. So here, the four valency of the carbon is associated by four different functional groups. And in this way, the C represents the chiral nature. Here the C represents the chiral nature and it is optically active and it represents the stereoisomerism. In this way, I suppose that you all are properly understand what is the chiral carbon. Now, the molecules having chiral carbon, if a molecules having chiral carbon represents two different forms and the form are called enantiomers. If in these two forms, these forms are referred as enantiomers. The term is enantiomers. Although the two enantiomers have the same physical and chemical properties. Physical and chemical properties of enantiomers are same. They have different biochemical properties. They have different biochemical properties. Although both represent the same physical and chemical property, they have the different biochemical properties. So, in here, the structurally, of course, here the enantiomers are the molecular organization and structural representation of the enantiomers are same and they represent the same physical and chemical properties, but they have different biochemical properties. Different enantiomers interact and bond differently with other biochemical molecules. And because it represents the in enantiomeric variation, its relationship or their relationship with the different molecules represent variation. If in examination or in question it is represented that what is the number of enantiomers in a possible number of enantiomers, then it is represented by 2 power n, where n represents the number of chiral carbon. For example, if we study the any carbohydrate, monosaccharide carbohydrate, and we observe that the molecules has the 4 chiral carbon. So the total possible enantiomers for that particular compound is 2 power 4. That is 16 possible enantiomers for that particular and it is the basic cause which is responsible for the more and more types of the hexose sugar, that is arabinose, galactose, glucose, fructose, mannose, all are the enantiomers of glucose. Now, it can be possible. How it can be possible? Because the monosaccharides have multiple chiral carbon and in nature it is commonly available in D form. Again, the activity with respect to the polarized light and the rotational behavior of the molecules is either clockwise or anti-clockwise. That means either dextro-rotatory or levo-rotatory. And in the nature, the monosaccharides are more abundantly present in dextro-rotatory form. So, some more terms, proper understanding of some more terms are necessary for the understanding of isomeric nature of the monosaccharides. The other term is the diesterone, diesteromers. Diesteromers is represented, diesteromers are not mirror image like the enantiomers, are not mirror image but differ in the configuration at one or more chiral carbon. In enantiomers, I am again repeating, in enantiomers, the components represent mirror image of each other. That is D or L, differing only at the chiral carbon center. In diesteromers, they are not mirror image. They are not mirror image, but differ in the configuration at one or more chiral center. Suppose in at one chiral stage, OH is represented in the left hand side and H is represented in the right hand side. In other, H is represented in the left hand side and OH is represented in the right hand side at the 2 points. So here it is not optically enantiomers, but they are diesteromers. Now the next term is the epimers, and epimers are diesteromers that differ only in the configuration at a single chain. Third one, next one is the anomers. In the term anomer is used for the variation in the spatial configuration in ring form. Just I am going to describe what is the ring form for the glucose. And without coming on the ring form, we are commonly representing in enantiomers or the isomer of monosaccharides in the open chain. If you go through the books, you observe that the glucose is referred as COH dash C dash C dash C dash C and sixth carbon is represented by CH2OH. And the first, between the fifth and sixth carbon, sorry, first and sixth carbon, all carbon is associated with OH and H. In one side OH is present, in another side H is present. And if you have copy at present, it is better to write that first carbon, you write the first carbon and you associated the first carbon with the aldehyde group, that is O and H. That is the aldehyde group, that is the first carbon, and again linearly you attach the second carbon, third carbon, fourth carbon, fifth carbon, and sixth carbon. Now you write the CH2OH with the sixth carbon, and you write, that means the four carbons remain, and you write OH in the one direction, H in the another direction, and you count that the number of the carbon, hydrogen and oxygen numbers are 6, 12 and 6. And here you observe that the four carbon, that is from the 2 to 4th carbon, second, third, fourth and fifth carbon, that is the 4 in number, represent chiral carbon. So it is the number of the glucose, it is the molecular formula for the glucose, and so we observed 16 types of the 16 different types of the hexoses. And if you try to represent, it is the linear representation. It is the linear representation, and the stereomeric representation or enantiomers represent structural representation of in enantiomers was at first represented by Emil Fischer. And Emil Fischer, a Nobel Prize winner, he was a Nobel Prize winner, a German chemist, it is well known, worker. And it represented a linear representation. It suggested a linear representation or line representation, and the method of representation is referred as Fischer projection. It is commonly referred as Fischer projection, because if we want to explain the spatial arrangement of molecules in the isomeric, to explain the isomeric nature or stereoisomeric nature, not the structure isomeric nature, then it requires three-dimensional representation. And Emil Fischer presented a method or a mode for the representing three-dimensional molecules by use of two-dimensional drawing. Then away from me, one bond, one is towards me, Second bond here and one molecule here. And here is the chiral carbon of the bond. So, by the two-dimensional nature, Emil Fischer represents the three-dimensional projection. Understand my mode is this. If you understand my representation, give me yes. If you have any problem, write problem, sir. No message. Can you hear me? Can you all hear me? No. No problem. And in this way, the diagram is drawn in the form of cross with the chiral carbon center at the point of intersection. Here the intersection is represented and it represented the cross section, and at this point like this here, that the chiral carbon is presented, that represents the intersection, and the one axis represented the horizontal line. Chiral carbon is represented by intersection. The horizontal line represents bond direction. Horizontal represents the bond direction outward toward observer, and the vertical line are bond pointing away. So in this way, or by the method of Fischer projection, we can represent the three-dimensional nature or a spatial and three-dimensional spatial arrangement by the use of two-dimensional representation. So here the representation and isomeric nature are studied, but and forms a ring-like structure. Pi bond associated with the second carbon is released and attached as the single bond in nature with fructose. In this way, both glucose and fructose form ring-like structure. And in the ring-like structure, when they obtain the ring-like structure, the structure detail as described by Howard, or the structure is also referred to the Howard, and the structure is named, Howard structure is named after the work of English chemist Sir Walter Howard. Here, the OH group associated with first carbon represents orientational variation in glucose. And on the basis of the orientation of the OH at the first carbon in the Haworth structure, it is divided into alpha and beta type. In beta type, it is represented in the lower part of the carbon, first carbon, and in the beta type, it is represented in the upper part of the first carbon. So, due to the orientational variation of the OH at first carbon of the Haworth structure into alpha and beta, the configuration also is also responsible for the variation in bonding nature. And now the glycosidic bond is formed if at the alpha carbon and alpha carbon, or alpha Haworth structure and alpha Haworth structure, with the alpha Haworth structure, it is referred as the alpha glycosidic bond, and if beta Haworth structure is associated, then it is referred as the beta glycosidic. In association with the polymerizing bond, so during the polymerization of the monosaccharides and the formation of the oligosaccharides and polysaccharides, the alpha and beta nature of the Haworth structure has significant role, and structurally if we consider energy level in the living system, the Haworth structure represent differences in the configuration, and the variation are referred as conformers. And if we study the conformers, the conformers are also represented conformational isomers, that is the conformational isomers, and they represent variation and observed as planar, half chair, boat, twist boat, and chair. These are the forms of the conformers. Or configurationally, the structure represents the variation. I am saying sequentially: planar, half chair, boat, twist boat, and chair. If we consider the energetics of the stability, then the forms are in increasing from least stability to most instability, and decreasing from most energy to least energy. That means if we consider the stability of the conformational isomers, then the planar is least stable and chair form is most stable. And if we consider the energy, then planar has the most energy and chair has the least energy.